Please go ahead, Maria.
So
Thanks a
can I
lot to be
start?
here.
Okay, very good. Thank you for inviting me. That's the last lecture of this series of 3 lectures I'm giving today. So this is more about the hints for new physics from precision physics. So yesterday and the day before, I talked most about standard model. So just saying, how much progress has been done recently in the calculation of the hard scattering of partons at the LHC, and also in understanding the structure of the proton. And today I would like to talk about how really precision physics, all this effort that goes on in QCD and in making our standard model precision as precise as possible, helps finding and understanding hints for new physics. Again, I will just give a personal selection of topics, okay? So I will start giving an introduction of what are the questions that one is trying to answer. And then I split the talk in 2 parts. So one part that is about direct searches and how QCD, just taking as an example of some works I've done on charge Higgs, how QCD can help um, searches, improving our reach and our understanding of direct searches for new physics. And the second part is about indirect searches. So it has more to do with um, a model independent parameterization of new physics that is done via these effective field theories, the standard model seen as an effective field theory. And talking about that, I will also mention at the end in the last slides a topic that it's quite dear to me, which is this need to go for simultaneous fits in order to have realistic determination of this kind of new physics. Okay, so let me start. Clearly, we have a number of many fascinating questions in front of us, because the discovery of the Higgs boson at the LHC was not the end of the story. Rather, it opens a whole new story and try to answer the deep questions we have. So in particular, the discovery of a scalar particle like the Higgs opens, the questions about the hierarchy problem. Why is there a huge gap between the Planck scale, which is 10 to the 19 GeV, where we know that there must be new physics for sure, and the electroweak scale, where we have the particles that we have discovered so far. And also, the Higgs boson is something that we just started to explore. Is it an elementary particle, a composite particle? Are there additional Higgs bosons around? And again, there is something that is in this nice paper by de Grassi et al. And that links the value, the precise knowledge of the value of the mass of the Higgs and the top with the stability or the metastability of the vacuum of the universe. So these are all questions that the very presence of the Higgs opens up in the hunt for new physics. Then, of course, as we know, this is probably the most recent results. We know that actually the baryonic matter that the standard model describes is only a tiny portion of what is in the universe, and that there is a large portion of matter which is called dark matter because it doesn't interact with light, and we don't know what it is made of. So none of the standard model particles are good candidates to be dark matter particle. So what are they? So there are several options, and the LHC tries to give answers complementary to many other experiments that are going on about dark matter. And on top of that, there is this whole beautiful flavor sector of quarks and leptons that we know for sure is like the particle evidence that there is something more, because the neutrino masses are something that was definitely revealed by the Super Kamiokande observation of neutrino oscillations, and that's something that, again, the standard model doesn't explain unless we have some heavy sterile neutrino. So are neutrinos Majorana or Dirac fermions? And again, the standard model doesn't explain what is the origin of the matter-antimatter asymmetry in the universe. And finally, last but not least, these recent hints for some flavor anomalies that were announced very recently and have been in all the newspapers, so that that could be explained by the same kind of physics. So on the one hand, there is this 3.1 sigma tension with the standard model in the measurements performed by LHCb in several observables. For example, this RK ratio of the decay of a B meson into a kaon and muon, or kaon and electron. So this ratio should be 1 in the standard model, but we know that the most recent measurement by the LHCb has found a value smaller than 1 that has a tension of 3.1 sigma from the standard model. So that's a very interesting sign that might hint to some flavor asymmetry, some new physics that prefers to couple to muon or rather than to electron or vice versa, okay? And also, this new formula result, was there a question? No, I don't know. I heard someone talk. Anyway, so these also other result that G-2 experiment of the muonic anomalous of the momentum of the muon that is 4.2 sigma tension with the standard model, with respect to the standard model prediction. There have been a number of papers in the past few days that try to explain that. And, definitely it's an exploration that has just started and it will go on for a while. So, how do we look for an answer to these fascinating questions that I mentioned in the previous slides? So there are two complementary kind of searches for new physics, and precision physics is important in both kind of new searches, because we can still hope that there is some new particle that can still be produced at the LHC that maybe has a smaller coupling, so we need more statistics to see it. But we might hope to see some bump in the energy region that we can explore now, or some deviation that hints to some particle that is here now. And to see a bump, you don't really need precision physics, but then to characterize what that bump is, so to characterize what you have, you definitely need precision physics. Or we might be in the situation that many people think is the most likely, in which the new physics is beyond the reach of the standard model. So it's at some energy scale which is much larger than the scale that can be probed by the Large Hadron Collider. And therefore, we cannot see any direct bump, but we would see deviations, especially in the tails of the high energy distributions that can be measured now. But clearly these deviations are more subtle, so we really need to have precision physics in the standard model and in the interpretation of these deviations to spot and identify from what kind of new physics this deviation come from. So here precision play a key role, okay? So let's talk very, briefly, give you my own personal overview of direct searches. So clearly this is still, a very active direction at the LHC. So both for theories and for experimentalists, because, when you have a collider that is reaching unexplored energy scales, such as the LHC, the searches for new physics should aim at being sensitive to the highest possible energy scale, and no stone should be left unturned, which is what is happening right now. So the strategy is look for new physics by covering the widest range of theoretically or experimentally motivated searches. At the beginning, the first thing that people were looking for were hints for supersymmetry, because this was the theory that was the most appealing from many points of view. So there have been a huge amount of direct searches for supersymmetric particles, so the super partner of the standard model particles. So each scalar paired up with a fermion, and each fermion paired up with a superscalar. And as you can see here, this is the update from July 2020 from Atlas. And you can see a huge number of searches that have been done in different, of course, simplified models sometimes, or in some direct model, depending on the search. And And these have set some stringent mass limits on squark, gluinos, stop, all these supersymmetric particles. As you can see, these lines that you can see here, these are the excluded regions. So this is what is forbidden by theory. This is what has been excluded by the experiment. So this has really pushed high up the scale of supersymmetric particles, which make people discuss about whether it's natural or not, the kind of supersymmetry that is left. But there have also been other exotic searches for models that are not just supersymmetry in its different incarnations, but also for extra dimensions, for Z prime or W prime here, for leptoquark, dark matter of different kinds. And again, you can see that the limits are pushing these particles to quite high masses, okay? So to really above the 1, 2, or 3 TeV scale, okay? But still, I think the experimentalists keep going and looking at corners of phase space that have not been explored in these kind of searches. One particular kind of direct searches that experimentalists at CERN have been focusing on is to look for a broader Higgs sector, because that would be the first sign of something bigger than what we know. So that's why the Higgs provides a privileged searching ground, because first of all, we just discovered it. It was less than 10 years ago. And some of its properties are either just been measured or completely unknown, like the self-coupling of the Higgs. And there is a plethora of production and decay modes available that, as we have more statistics, we can investigate. And also the Higgs is special because it's the first elementary scalar particle ever seen. It carries this new kind of interaction, the Yukawa force, whose effects still need to be measured below 10% accuracy. So I think there are several motivations to have a richer scalar sector with more doublets or high representation for the Higgs. So the Higgs could really be the first of many new scalar states. One possibility that incorporates several models beyond the standard one is the 2 Higgs doublet model. So that's a simplex extension of the standard model Higgs sector. You have 2 Higgs doublet, and this leads, so each of them has a different vacuum expectation value, V1 and V2. And the ratio of these 2 expectation values can be parameterized by this tan beta. And this leads to 5 physical Higgses. So one of the neutral, typically the H small, has the same properties as the standard model, but on top of that, there are other Higgses that are heavier than this one, and 2 charged Higgses. So many of the searches have been focused on charged Higgs, because clearly if you see a charged scalar particle, that would be an unmistakable sign of a broader Higgs sector. And here I just want to show you in this kind of search how the fact of having a fully automated simulation chain has really improved these kind of searches, and how precise QCD calculations are and have been key in order to improve the exclusion regions in direct searches for charged Higgs. So what is there, not only for charged Higgs, but for all kind of direct searches, is really that when you have an idea, there are all these automated tools, you can incorporate it into a Lagrangian. This gives you some Feynman rules. You put them in a Monte Carlo generator, and you can generate both the signal and the background, generate the events, and compare these to the experimental data. And I just want to show you how these worked and the work that I've done in the charged Higgs sector. So if you look at what are the main production mechanisms for charged Higgs at the LHC, if this charged Higgs has a mass that is smaller than the mass of the top, then it's typically produced off a top quark in the final state. So this is the kind of signal that experimentalists look for. And I'm talking about the status in 2015 and how it has improved throughout run 2. So these, we already had some precise predictions for that, okay? But if the Higgs, the charge Higgs was heavy, so the mass of the charge Higgs was larger than the mass of the top, then there is an ambiguity in QCD in a sense that this can be described via two schemes, the ones that I was mentioning in my first talk. So the 4-flavor scheme, where the bottom quark, which interacts with the top in order to produce this charge Higgs, is produced in the final state, or the 5-flavor scheme, where the bottom quark, which interacts with the anti-top to produce the charge Higgs, is in the initial state. So it's inside the proton. And there was a large theoretical ambiguity, a large theoretical uncertainty that experimentally we're associating to the different calculation in the two schemes. And therefore, the bounds that we were having were not so precise as they could be because of this uncertainty that was coming from an imperfect understanding of QCD, if you want. And also the region of intermediate charge Higgs masses for charge Higgs mass close to the mass of the top. There were no searches done in run 1 due to the lack of some calculation in the region where the top is close to resonance that were giving some predictions for this signal. So this situation has improved thanks to precision physics, if you want. So I just tell you just a few results that helped in better modeling the signal for charge Higgs in these two regions that were not really well known in 2015, and how this has led to more precise results for that. So, as I said, when you look at the production of a charged Higgs as a result of the interaction of top and bottom, you have these two calculations. So this is the leading order diagram for the 4-flavor scheme, and this is the leading order diagram for the 5-flavor scheme. Clearly, if we have all the orders in perturbation theory, and you could, that would give similar results. But at different orders in perturbation theory, they were giving very different results. And if we look at the differences here between one scheme and the other, this one has the advantage. So when you have the bottom quark only in the final states, you have the advantage of having mass effects of the bottom core there at any order, and it's straightforward to implement it in a Monte Carlo event generation at leading order or next to leading order. However, it doesn't sum these logarithms that might be big. So I go back to the argument about resummation that I made in my first talk, okay? So whenever you have logarithms that can be large, because the numerator of the logarithm can be larger than the denominator, then you have better resumming them. And this is done automatically in the 5-flavor scheme, okay? So what we did with many collaborators and people working on that was, first of all, that looking at the inclusive cross-section, so the total number of events for charge Higgs production, we looked at and basically what we found out in this paper is that actually for all values of charge Higgs masses, the 4-flavor scheme and the 5-flavor scheme are not too different, as long as you compare them at the right value of factorization and normalization scale. Because basically the natural scale of this process is much smaller than the mass of the final states. And that's something that was studied in this paper with Fabio Maltoni and Giovanni Ridolfi. So I think this helped in reducing the theoretical uncertainty, because there was a reason within QCD to choose a smaller scale for this process. The other problem that theorists had to solve in order to improve the searches was when you were looking at the signal shapes. So whenever you had the signal shapes in these two schemes, 4-flavor and basically the only scheme that was implemented in the Monte Carlo event generators that experimentalists were using to compare to the charged Higgs signal was the 5-flavor scheme. And the 4-flavor scheme was only at the leading order. And these two were leading to very different distributions for the signal. And this was the biggest source of systematic uncertainty in the experimental prediction. So this is the systematic uncertainty in the searches that was coming because of this difference, okay? So what we did thanks to Céline Legrand, Marius Wiesmann, and Marco Zaro, we looked at how to implement this 2 Higgs doublet model that was leading to the production of charged Higgses in both schemes, not only in the 5-flavor, but also in the 4-flavor scheme, in this MADGRAPH 5 AMC at NLO. But to do that, we really had to do the FKS method for infrared subtraction. So there are all these technicalities that I was mentioning in my first talk. And we had to include all sources of uncertainties, and we had to rely on models resulting into a set of Feynman rules generated automatically thanks to this tool that is described here. And also all the counter terms had to be automatically generated. And tested and validated. Anyway, we could finally look at the distribution in terms of several variables that were measured experimentally, like the PT of the top quarks. And actually, doing this comparison, we could tell experimentalists, what was the best way to simulate this new physics signal. So in particular, looking at the both schemes at NX leading order was bringing the two predictions closer. So the systematic uncertainty that comes from theory was reduced strongly. Second, we realized that whenever we are looking at bottom quark, the 5-flavor scheme was suboptimal because it was leading to larger uncertainties. So this is the distribution of the PT of the second bottom quark. It's a very crowded plot, but I just wanted to show, this is the K factor basically, and these lines here, which are the green and the black, are the one of the 5-flavor scheme. So you can see that the K factor is much larger. And also we found out that you have a much more strong dependence on the 5-flavor scheme calculation to the matching with particular parton shower model. So as a result of this investigation, we could conclude that for this kind of process, it was better to simulate it in the 4-flavor scheme because it was much more convenient to look at B exclusive observables. And this is something that was used in the analysis and really improved a lot the region of exclusions of charged Higgs boson, because of course it was not found. Also, another thing that goes in the same direction is the study of intermediate mass charged Higgs, because again, this region where the mass of the charged Higgs was between 160 and 200 was not studied in run 1, because the leading order total cross-section for the signal had a very large theoretical error. So one needed to have the next to leading order calculation. And that's something that with Richard Frederick and some other people we determined. So using the complex top mass and Yukawa scheme, we could include this intermediate charged Higgs that is close to resonance with the top. And this is something that gave some precise next to leading order predictions that bridged the gap of the predictions that were there. And as a result, now you can see that whenever the bounds, so for what region of the tangent of beta and the mass of this charged boson is excluded, now the whole region of charged Higgs masses is covered, and these regions that you can see colored here have been excluded to 95% confidence level. So this is an effort that goes on, but I think it's a very nice example of how a good understanding of QCD is important, not only in the background, but also as far as the signal is concerned. Very good. So now I move to the second part of my lecture, which is about indirect searches. I don't know if anybody has questions, but I can stop here to answer your questions. If not, I can move on. And I drink. Okay, so I don't hear any questions at the moment, so I will go on, but please do feel free to interrupt me at any point if you have questions. Okay, so now I talk about the second kind of new physics searches, and again, how phenomenology can help in this very, very big and important effort. So the instrument that is used in order to do indirect searches, so one of the main theoretical instruments that is used is the effective field theory approach, okay? So the effective field theory has the advantage of being a model-independent approach for looking for physics beyond the standard model. Of course, you have an assumption, so you assume that the new physics states are heavy, they are much above the scale that can be reached by the experiments, in particular case by the LHC. But the trick is that basically you can write the Lagrangian. So on top of the standard model Lagrangian, you add bits with higher dimensional operators that have only light standard model particles. So the field content of these operators are only light standard model particles. And the BSM effects can be incorporated as a momentum expansion in terms of these higher dimensional operators, okay, with the usual convention for the dimension of the field. So a vector and scalar field have dimension 1, fermion fields dimension 3.5, okay? So just to give a very brief sketching on how this works, imagine that you have some UV model that implies the presence of a Z prime, so a new vector boson of mass m, which is much larger than lambda, which is the cutoff scale that is above the energy that can be reached at the LHC, which is here, which is about the electroweak scale. And of course, if this particle existed, we would observe at loop level or as an off-shell propagator at tree level, okay? So it could propagate here, but of course, because the mass of this particle is much larger than the momenta that can be an exchange between particles at the LHC, you can do an expansion. So you can Taylor expand this propagator. So you have the first term, which is a leading order term that is suppressed by m squared, so the mass of this heavy state. So what happens is that now, if you write the final rules for that, on top of the standard model Lagrangian, you have an extra operator that is a 4 fermion contact interaction here that is suppressed by lambda, so the scale above which you have the new Z particle, and has some coefficient C, where this coefficient depends on the interaction that the Z prime particle has with the standard model particle. So it depends on this interaction once we integrate out this field from our Fock space. So this is the trick, no? But of course, we do it in a model-independent way. So using dimensional analysis, you can write the most generic basis in dimension 6, dimension 8, and so on. Of course, the higher the dimension, the trickier it is to write the most generic local operator set. But that's a trick. So the BSM effects are all incorporated in the coefficient and the scale that suppresses this coefficient, and the operators are all made with standard model fields. So what is very beautiful, what is powerful about this approach is that beyond the standard model comes as a perturbation around the standard model. And the EFT reveals high energy through precise measurements at low energy. And clearly, what is also nice is that this thing can be expanded not only in 1 over lambda, but also in according to the usual perturbative expansion in the QCD coupling and in the electroweak coupling. So each operator can be improved at higher orders, including QCD and higher order electroweak corrections. So what we normally, so one of the effective field theories, you can use many of them, but the ones that at the moment is the most popular at the LHC is the standard model effective field theory, which basically has all the 4 ingredients of when you study the standard model, but it gives up the renormalizability. So basically it's the basic framework is that of a described by a local Lagrangian. The Lagrangian is invariant under the linearly realized local SU3 times SU2 times U1 symmetry. And the vacuum state of the theory preserves only the SU3 times U1 local symmetry as a result of the Higgs mechanism, okay? And the spontaneous symmetry breaking happens through this doublet 1, 2, which is the Higgs, which is invariant under local symmetry. So the only thing you give up of the usual assumption normalized, which means that all interactions up to canonical mass dimension 4 are allowed in the Lagrangian, okay? So there are theories that are more like, there are EFTs that are more general with respect to that. For example, the Higgs effective field theory gives up this. So in a sense, you still keep the same gauge symmetry as the standard model, but you allow to have something more complex than just one Higgs doublet. Different choices that one can make in building up this set of higher dimensional operators that parameterize new physics. Different choices lead to broader or smaller spectrum of operators, okay? So let me just focus on dimension 6 operators that you add in the standard model effective field theories, which is built upon the assumptions that I listed here. So how many operators you have if you write a basis of the space of operator under this assumption? So this alpha, if you write the complete basis of SU3 times SU2 times U1 invariant dimension 6 operator constructed out of standard model fields, you have nearly 2,500 operators after imposing the baryon and lepton number conservation, okay? If you assume something about the flavor structure, so if, for example, you assume flavor universality, this big number goes down to 76 operators. And yes, that's it. So depending on what you're interested in, or what are your assumptions, which come from your prejudice about the BSM complete theory, this number of operators can be reduced. But if you keep them all, like for example, in this Warsaw basis that I wrote here, you have quite a large number, you know, so 2,500, because each index here gives you a different kind of operator. Okay, so all these flavor indices that you have here, I won't go through all of them, just to flash you what is the structure of these, for example, 4 fermion operators with different tensors in between, or this operator of interaction between the gluon fields and so on. Okay, so you have plenty of them. So how do we constrain new physics in this model-independent way, which is done by this standard model effective field theory? So using this operator, in particular, looking at their interference with the standard model amplitude, you have that every observable can be written like the observable in the standard model, plus some corrections that are suppressed by this lambda scale of new physics, are proportional to some coefficient, and are somehow S, and grow sometimes with the energy. Okay, so this S is not something universal, depends on the process and the operator. So it's true that it's a very large number of operators, but it's also true that there is a plethora of observables and final states to measure at the LHC. So as you can see here, we have that the precision observables are in the bulk of the distribution. For example, where you are close to the shell of the mass of the Z over the W. The tails, because of these energy growing effects of the operator, are the ones that have the largest sensitivity to this operator. Of course, there is, because all this SMEFT construction is based upon the idea that we are not going above the scale of new physics. So we have always to be careful that the measurements that we are looking at do not exceed the cutoff of our effective field theory, which is lambda, okay? So this is in general. So basically, how do we actually constrain this operator? Because, for example, if we were finding from these fits some operator that is not compatible with zero, this would be a discovery of new physics effect that then has to be identified and linked with the UV completion, okay? If we are all of them compatible with zero, we have some constraints on how big can the new physics effect be. But you really need to have a global constraining strategy in order to do something with these fits. So in particular, if you want to look at a class of this operator, you have to identify which of those operators enter the theoretical prediction for each observable at leading, next to leading, next to next. You have to find enough observable to constrain all the operators. And you need to, basically it's like what I was saying for the fit of the PDF, but now I'm talking about the fit of this coefficient, this Wilson coefficient of this SMEFT expansion. So we really need precision in the standard model part of the calculation. We need to automate the calculation of this SMEFT correction. And we also need to have tools and calculations that connect the bounds that we find at the level of the Wilson coefficient to the actual UV completion, to the actual BSM scenarios. And that's something that many people are working on, and a huge progress has been made in the past few years in that, so not only in the theoretical aspect of determining what are the bases for that, how you go from one basis to the other, but also in really developing these fitting tools that allow us to globally interpret the measurement in terms of these coefficients. So however, so far nobody has ever fitted the 2,500 operators. So you only, most of these SMEFT fits that are very, it's a very active field, they are restricted to a few observable and sectors. So sometimes they only look at the Higgs or only at the top measurements. So this reduces by a lot the number of dimension 6 operators involved. The biggest fit that has been produced so far is this one that came up very recently, like a couple of months ago, that includes 34 dimension 6 operators. And in terms of observable, it looks at deviations in the electroweak precision observable, dye boson production at LEP and at the LHC, LHC run 1 and run 2, Higgs and Tevatron, and LHC top data. So they use 300 measurements, more or less, to constrain 34 Wilson coefficients that are in front of these dimension 6 operators. And as you can see here, this is, I think I took it from their paper. You can see that so far, all the operators are consistent with zero, but that depending on what you're looking at, they're more or less constrained. So as we go on with that, with this kind of analysis, it's very important to look at what is the picture that comes out of that, because different combination would hint to different kind of physics beyond the standard model. Okay, the very last topic before concluding my lectures will be this topic that I'm particularly passionate about. It's this ERC that I'm working on with my collaborator is all about that. It's about the need for simultaneous fits. Because let me first make a very short digression, because that's the most obvious simultaneous fit that you can think of. And then I go back to the searches for new physics. So in the very first lecture, we went at the scale mz from different processes. And some of these processes are happening at the LHC. So I showed you explicitly how from the agreement, the data theory, you can extract a parameter, which is alpha. We know very well that the pattern distribution functions of the proton, which I discussed in great details yesterday, and alpha S are very strongly correlated, because the PDF evolution with the scale PDFs, so processes that do not involve the proton in the initial state. But people can also look at these processes like this determination you can see here. And the advantage of determining the alpha S together with the PDFs has the advantage that is driven by the combination of the many experimental measurements I was showing you yesterday from several different processes. So, for example, what you can do is to do a scan, like the one that we did with Richard Ball and collaborators about 10 years ago. You can do a scan over alpha S at the mass of the Z and look at the chi-square of the data that you include in a PDF determination. And this determines a parabola. And from here, with delta chi-square equal 1, you can find what is the preferred value of alpha S from the data, okay? You can do that in this simple way, or you can include the correlation between the PDFs and alpha S, and this changes the result. And you can find the details in this paper here if you're interested in. But my point is the following. There was this paper by Stefano Forte and Zahari Kassabov very recently that was showing that the result you get for alpha S, if you take it from a global fit in which you fit both alpha S and the PDF, you get one number that is in line with what you find in the PDG average. But if you instead only fit one particular data set and you do not fit the PDFs at the same time, you find an inconsistent result. So what is written in this paper, I think it's very important, because it said that any determination of the strong coupling constant from a process that depends on parton distributions doesn't lead to the correct result unless the parton distributions are determined simultaneously along with this parameter. So I think this result points to something that is much more general than just PDF and alpha S. I think it points towards the need of a new generation of global fits in which all the precision ingredients that enter theoretical predictions are treated in a consistent way. So let me tell you why I believe that, and let's see if this is the case also when you look at the SMEFT fit of the Wilson coefficients and the PDFs. So let's go back to what I said yesterday and link with what I said today. So yesterday I told you that in order to determine the parameter of the PDF, so the parameters that determine the structure of the proton, what we do is that we compare the LHC data to the theoretical predictions, assuming standard model, and we determine the fit of the PDF coefficient theta k, okay? What we do in this SMEFT fit, I just talked about, again, we take the LHC data, we assume standard model PDFs, and we fit the deviations of from the standard model, which are parameterized by the Wilson coefficients Ci. Okay, so in one, we are assuming that the cross-section are standard model. In the other one, we are assuming that the PDFs are standard model, okay? But the data, unfortunately, that enter this fit do overlap quite significantly because, for example, the top data that we use in the PDF fits is MEFT analysis for top related coefficients, or the many JETS data that we include in a PDF fit are also used for determining some of these Wilson coefficients in the MEFT expansion. And the same for Drellian data. So the Drellian data that go up to high invariant mass that are being measured at the LHC are also measured in this MEFT analysis. So you see here that there is something to understand because we might do things in an inconsistent way. So the question is, how do we disentangle the effects? I think it's the question that Francesca was asking yesterday. So shall we get rid of all the data that probe a high energy regime, and we keep these only for the PDFs and this data only for the SMEFT analysis? Or can people think of doing some simultaneous fit of both? So what if you do not assume the standard model in the PDFs nor in here? So you let the Wilson coefficient vary both here and there consistently, because it's the same cross-section we're talking about, and you look at the interplay between the two. So this is something that I investigated with some of my collaborators in these two papers, and I just want to show you, flash you some results that we can discuss about if you're interested, or you can have a look at later. So in particular, we looked at the high energy Drellian tails, because that's a place where many people look in order to find hints for new physics. No? So very often we have so they're important because this data constrains the quark anti-quark luminosity, and new physics could distort details. So it's a nice place where to ask about the interplay between new physics and PDFs. In particular, we look at the kind of simple scenario where we only have two coefficients, which are this W hat and Y hat, which have been studied by Riccardo Torre, Andrea Wulzer, and collaborators in this paper. They are these parameters that can be linked to dimension 6 operator in this MEFT that basically parameterize the self-energy of the electroweak gauge bosons. There are four of these operators, but these S hat and T hat have a weaker dependence on the energy scale, and they are very well constrained by LEP. Instead, for W hat and Y hat, there is much more room for new physics at the LHC. And in fact, there was this very nice paper by Riccardo Torre and collaborators in which looking at the projections for the high luminosity LHC, one can show what can be the constraint on this kind of operators. But in this analysis, like in all this MEFT analysis, PDFs are assumed to be standard model-like. So what we did in this paper with my collaborators in Cambridge, we looked at the standard procedure, so assuming standard model PDFs, and look at the data theory agreement as a function of the Wilson coefficients, or instead we compare by SMEFT PDFs. So for each value of the Wilson coefficient, we do a consistent fit of the PDF. So we simultaneously fit the coefficient in the PDF fit and in the fit of the SMEFT. So to do that, we include all the deep inelastic scattering data and the high mass Drellian. So at the moment, there are 5 data sets of high mass Drelian that we routinely include into PDF fits. Plus, we also looked at some projections for the high luminosity LHC. We use the most accurate standard model, the predictions for the standard model, and we include the K factor to include the SMEFT. And what we find, I think it's very interesting, because with the current data, the interplay is not really much, in a sense that if you look at the bounds for the Wilson coefficients for W hat and Y hat using standard model PDFs or doing the simultaneous fit, everything is within the PDF uncertainty. So it's not a big deal. But if we look at the high luminosity projection, if basically you take the high luminosity data, you include them in the PDF analysis, pretending that they do not have any effect, they are just standard model, and you use them to do the Wilson coefficient fit, you find very different results, because these ellipses is what you obtain by using the standard model PDF, so in an inconsistent way if you want. But if you fit them all simultaneously, you find a much broader ellipses. So basically the constraints on your physics, it's much weaker. So neglecting this interplay between PDFs and EFT would lead to a significant underestimate of the uncertainty on the EFT parameters. So basically, this is the kind of final result that we added, we showed in our paper, is that basically the small bounds that you observe here, for example, for W hat, are due to a significant underestimate of uncertainty. And if you do a consistent treatment, you only have mild improvement with respect to the current bound when you go to the high luminosity LHC. So I think that's a very interesting result to keep into account. Very good. So to conclude, I hope that in these lectures I showed how fascinating are the challenges that precision physics opens up at the LHC and beyond. And that really we need precise and accurate theoretical predictions to make progress in our analysis. Today, I showed you how QCD precision physics helps both direct and indirect searches. And also, I hope I showed you that it's what is really needed, what is something that is worth focusing on now, is really to have a robust statistical framework to globally interpret all subtle deviations from the standard model that might arise in the next few years. So if the 2 terms, which are precision and discovery, have characterized the LHC it will become even more predominant in the years ahead, and that's going to be very, very nice. So thank you so much for your attention. And
thanks to you.
I have a question. Yes. First of all, thank you very much for your very nice series of lectures. I don't work in this in phenomenology, so idea of the recent developments in these themes. My question regards these terms, the many terms appearing in the effective field theory, which are compatible with symmetries. You said there are a few thousands, 2,000, 3,000, which are compatible with the SU3 cross SU2 cross U1. But are they selected? I mean, and it's important to decrease the number, as you said. Are there, I mean, the relevant, possible relevant ones are not reduced by the fact that these terms should also be compatible with symmetry breaking and with minimal coupling. or not? Is it taken into account this problem or not at this point?
Yeah, so yeah, I think that these 2,500 operators that you get at dimension 6 already, you impose the gauge symmetries of the standard model and also the spontaneous symmetry breaking that happens linearly via a SU2 doublet. So this is already included, otherwise you would have more. So for example, I think in the Higgs effective filter, you have more operators there. But what reduces that is the assumptions on the flavor. So I think that's why if we have strong reasons to believe, for example, that the theory that we want to parameterize is flavor universal, this number reduces. Or if we, for example, look only at one generation, or I don't know, sometimes you say, what if we look only at one generation? Because, for example, new physics is manifest only in the third generation of quarks. Again, this reduces the number enormously. So I think that there is a lot of...
And also, I guess that if you start from a more complete theory with heavier particles, but you minimally couple them to the vector bosons, the number of independent terms you get is largely reduced.
Yeah, that's true. Yes, absolutely. There are assumptions you can do in the UV model that propagate down to the number of operator and reduce it. Also, another field that I'm not an expert, but...
And this is taken into account already or not?
No, by default, no. It's something that you have to look at the full set and then assuming that you can reduce the number. Another is if you, for example, in the UV, you assume the analyticity of the amplitude or the positivity of the amplitude, and you also get additional constraints. That's a very active field. I'm not an expert, but it's very fascinating, I think.
I see. Thank you.
Thank you for the question.
Any other question? I have a question exactly on this transparency. More than a question, is a comment. I think one of the most beautiful features to use this standard effective field theory is the Weinberg approach, because if you want one of the properties of the standard model is that baryon and lepton number conservation come up as accidental symmetries. Indeed, if you don't impose that as you did, you have dimension 5 operators, and is a natural way to have lepton number conservation and neutrino masses.
Yes.
Is a beautiful way to predict neutrino masses. This is way the Weinberg arrived to these dimension 5 operators.
Yeah, I agree exactly. So yeah, I had it in the backup because I didn't have time to mention it.
No, it's okay.
It's
your way is the orthodox way. So
yeah. It also shows, is it that now why the lepton, in a sense, the constraint on the lepton number is weaker because it's suppressed by lambda instead of lambda to the second for the baryon number to violate the baryon.
Of course, yes. Then of course you have the other problem that you have to suppress proton decay, and then this is a good way. Yes. So
yeah.
Indeed.
No, you're right. That's a super important observation.
Also flavor universality, because if you want actually, I think Wheeler told me that the reason that they studied these bases, the Buchmuller and Wheeler, is because they want to understand flavor. So they want to understand how the interplay between flavor and electroweak data Indeed, that's why you said it. And also now is interesting the play, the way you said it too. Because actually, one thing that I wanted to say now is very important, because if it's true, these B anomalies, violate the lepton flavor universality. Then you have to abuse flavor universality, and you have to introduce new operator. Indeed, your collaborator Greyo and also us introduce some operator to see if at colliders you can have a counter check.
It's true. Yeah, there are lots of works that I didn't have time to mention, but I'm also studying right now, that we introduced this generic operator for lepton flavor violation, lepton number violation, universality in a broader context, because they show up also in other observables, not only in the ones measured by the LHCb. So in this context, I agree, totally agree with you. It's very important to look at the full picture.
Any other question to this beautiful lecture? Francesco, comments?
Hey.
Yes, she's looking forward to your observation.
No, I don't know. It's a big amount of information. Actually.
Did you? She didn't discuss your leptoquark limit.
If she is aware of, I don't know if she's aware of. I wanted to ask, but I don't know. Actually, it's very interesting because we have now, next week, we will meet the Atlas group that is willing to perform this search. I don't know, Maria, if you have seen this, the creation of a leptoquark in the collision of a lepton in the proton and the quark in the other proton, so in the S channel. So this is what we proposed.
But I heard about it, but I haven't read the paper. But it's very interesting from my perspective because of lepton PDFs.
Yeah, we made first this derivation with Paolo Nason.
Exactly. So it's a Lux QED applied to the leptons.
Exactly.
No? So,
yes.
Yeah,
it's the same idea, but it's slightly more involved because you start from the quark and you want to arrive to the lepton.
Exactly,
so
but it's
the
very
matching
important because in doing from the data, you have a huge error band. There was this work by Bertone and other people. Instead, if you calculate it as you do, you have a much smaller error band because
exactly,
you do it analytically, no? That's what
yes,
I understand.
Yes, exactly.
Yeah.
And this makes things interesting because we put forward this idea of studying the leptoquark in the S channel, but then as soon as we push the article on the archive, I think, yes, somebody, I will not tell who, came mentioning another paper proposing to do this, but 20 years ago. So it looked that, we have lost this. But the point is that they had a way to derive the lepton PDF that was totally wrong because there was this logarithm of the scale of the process over the mass of the electron, over the mass of the... So
and not just big logarithm, huge logarithm.
So it was just an heuristic reasoning, let's say.
That's how they discovered the PDF scaling was wrong.
And so this and while instead our approach allowed to make the precise,
No, but I think that
precise quantitative.
the motivation was completely different. I think 20 years ago, the argument was at Terra. They wanted to discover laptop work at Terra.
No. There was this paper with very few, because it was not possible to assign an error for this reason. Because you cannot assign a real error. So it's not even improved the Parton model. It's nothing basically. So that's why it was not pursued. But now with the Lepton PDF that gives, I don't know, kind of a few percent error.
Yeah.
If you do even a next leading order computation has been done after our work, somebody else has done also the NLO correction. So now the things is meaningful. You can put stringent bounds on the existence of laptop works produced in the S channel and the LHC. So you can see the LHC as a no, it's amazing also because we have been taught since the elementary school that you have proton and electron around, while we
Inside,
we
yes.
also have electron inside.
It's true.
So
Nice.
but okay.
No, so I was prepared. I didn't have any questions as well because
No, we take advantage of you because we have been in the cage for 1 year. So now is a good chance to come out.
Thank you.
Any more question to Maria, since she's so nice to answer, or she's very patient? Gaetano? No. Okay.
I have already asked.
So Gaetano, do you have more question?
I'm learning, I'm hearing, listening very
Yeah.
much. It was a very good series, I said. Yes, I enjoyed it.
Thank you.
Okay. So this was your last lecture, if I see.
Yes. I really used your patience enough. Yeah, it was the third one and last.
So tonight we'll go for pizza, I guess.
I'm not in Naples, unfortunately. You know, when you
What a
invited
pity,
me, I was
yes.
dreaming to be there, but I'm still here in Cambridge in my cage. So it's yeah.
What a pity.
Yeah.
Yeah.
But you have good Indian food, so you know, so that's
It's not the same. It's a personal choice.
For the time being, we are in cages and many animals are free to go around in the sea. You know, there is, in the last week, a beautiful whale has been seen and even touched